Hi everyone, I'm Pavlos Petoumenos and this is our work on fast-focused function merging. The main author is Sean, who did the core of this work for his undergrad thesis with me and Rodrigo supervising. So, reducing size is getting increased interest. Whether due to the cost of storing the code or due to the cost of downloading the code, we want to minimize code size. Our work in this area focuses on function merging. The central idea is to find similar functions and replace them with a single function that provides the same functionality but needs less space. In this example, with functions A and B, we first use sequence alignment, a bioinformatics algorithm, to identify similar parts of A and B that can be merged, marked here with green. And then we produce the merged function. The similar bits are combined, with the same code providing the functionality for both A and B. The dissimilar bits are copied into the merged function. First A, then B, but their execution is conditional on a function identifier which indicates which of the two functions was originally executed. If the new function is smaller than the sum of A and B, we replace them with the merged one and save space. But before we get there, we need to do a few more things. We need to find similar function pairs, then to find similar block pairs in these functions, align their code with sequence alignment, and only then we try to merge them. That first step, function pairing, looks straightforward, but it is in fact the single biggest problem with the current state of the art. Not only it's extremely slow, it's also surprisingly bad at finding similar functions. Regarding its speed, this is the breakdown of the runtime of the function merging when we apply it on a relatively big program like the Linux kernel. The whole process takes more than 2 minutes. 85% of that time is spent on ranking functions based on their estimated similarity, which is something we have to do to find similar pairs. That's the two green bits. And despite all this effort we're putting, all this time spent ranking, most of these pairs are not actually very good. 93% of the ranking time is for finding unprofitable pairs. Pairs that we align, then merge, and then we discard. This becomes even worse when we apply function merging on a really big program like Google Chrome. The 2 minutes for Linux were already a bit too much, but now merging takes almost 2 days. Practically all of it is ranking time. Which is ironic given that F3M, the state-of-the-art algorithm, was supposed to have no overhead. The authors even put that in the title. Let's dive into how exactly ranking works. For each function, we produce a fixed length representation, a fingerprint, indicating the frequencies of different instruction opcodes in the code. In the simplified example, we only have 10 functions and the fingerprint captures frequencies for only 5 instruction opcodes. For each function, we compare its fingerprint to the fingerprints of all other functions. Green indicates the common parts, light and dark red indicates their differences. The function with the most similar fingerprint, the one with the smallest Manhattan distance, is then selected. In this case, it's function 3. This is a simple process, but the time complexity of the overall ranking stage is almost n squared. For each one of the n functions, we have to compare fingerprints with n-1 other functions. This is okay for smaller programs, but it causes the explosion of ranking time we saw for larger programs. A second somewhat related problem is the fingerprint itself. While it is easy to produce and fast compare, it is not very helpful for finding similar functions. This is a heat map showing fingerprint similarity and how well the functions actually align for all 800 million function pairs in Linux. The darker the color of each square, the more function pairs have that fingerprint similarity and alignment. Similarity and alignment go from 0 to 1. 0 is no similarity, 1 is identical function or fingerprints. The two metrics are not completely unrelated. Highly similar functions that align well towards the top of the plot always have high fingerprint similarity. The opposite is not true though. Functions with highly similar fingerprints towards the right side of the plot are unlikely to align well. As a result, the correlation of the two is only 20%. And this is why fingerprints do such a bad job. That's perf trace destroy, a Linux function, in its IR form. Let's simplify it a bit to make some space. Here, and under it we have its fingerprint. 1 bit casts, 4 calls, 3 get element pointers, 3 loads, 1 return. The most similar fingerprint in the whole Linux codebase is that of FAT put super, with a similarity of 92%. But it's actually an awful match. If we align the two, we get something like this. Green shows what can be merged, red what cannot. Only 7 instructions are aligned, an alignment of 39%. The main reason for the gap between the two metrics is that fingerprints do not capture the information we actually care about. For example, the 4 calls on each side have the same instruction type, but they're not mergeable because they have incompatible arguments and types. The bitcast instruction, on the other hand, has the same arguments and types on both sides, but it is still not aligned because it is in 2 completely different parts of the code. The context of the instruction matters, where the instruction is in the code matters. What is actually the best match is this one, the perf kprob destroy function, very similarly named. The fingerprint distance is 2, and the similarity is 86%, but the two functions are almost identical. The only difference is that perf kprob destroy has 2 extra instructions just before the return, so alignment is 86% too. A good similarity metric should be able to tell that this is the best match. Our approach, F3M, aims to solve all these problems and provide fast matching using a similarity metric that captures code structure and use all the information that is relevant to decide whether 2 instructions are mergeable, not just their opcodes. We will do this by using locality-sensitive hashing, a type of approximate nearest neighbor search to speed up ranking, by using min hashes to capture information about the function's internal structure, and finally by using an instruction representation that aligns with what matters for merging. We'll start with that last bit first. The fingerprint of -m, the state-of-the-art, sees functions as a vector of opcodes. All other information is discarded. Our approach instead represents its instruction as a number, which is encoding what matters the most for merging. This is of course the opcode, but also its input types, its result type, and other criteria that are specific to each instruction type. Instructions with different representations are guaranteed to be not mergeable. For example, the 3 calls that -m treats as identical here get different representations and are treated as different instruction types. The next bit is to capture more of that structure of the function. Back to our perf trace destroy function in its numerical representation, this time compared against a fake function called foo. Here structure matters. The two functions have mergeable instructions, highlighted with the same color, but they are in the wrong places. At most, only 2 instructions can be aligned, and even then, merging those isolated instructions is rarely profitable, so they probably will get 0 benefit from merging those functions. We are not the first people to have this kind of problem. Quickly approximating the degree of structural similarity between 2 texts or 2 DNA sequences is essentially the same problem. So we take inspiration from these areas and we compare the 2 functions in terms of overlapping tuples of instructions, in terms of n-grams, or in terms of k-mers. In our example, we would produce trigrams, n-grams of size 3, like this. First, instructions 1 to 3 go to the first n-gram, then instructions 2 to 4, 3 to 5, and so on, until we get the end of the function. Then we do the exact same thing for the other function, producing 2 trigrams. And to reason about the similarity of the n-grams, we treat the functions as sets of n-grams and see how many of them are common in the 2 sets and how many are not. We would basically calculate the Jacquard similarity, which is the size of the 2 sets intersection divided by the size of their union. In our example, similarity would be 0 because the 2 functions have no identical trigrams. And this is a better similarity metric because it captures some of the structure. It's not enough to have identical instructions in the 2 functions. We need to have identical groups of instructions to have any kind of similarity. While a good metric, it is costly to calculate, but we have a fast approximation for that through min hashes. Starting with the n-grams of each function and using the same set of k-hash functions, we apply them on each n-gram, producing k-hash values, and for each function we choose the smallest hash value it's produced. First, this value corresponding to the second n-gram, this value corresponding to the last n-gram, this value corresponding to the first n-gram, and finally this corresponding again to the second n-gram. The point of this process is that it kind of samples, somewhat randomly, the input set of n-grams. The vector of values at the output, our min-hash fingerprint, indicates with high certainty the existence of specific n-grams in the code. So, if 2 min-hash fingerprints include the exact same value, this is a strong indication that they have the same n-gram in their code. If the whole fingerprints are identical, it is likely that they include the exact same sets of n-grams, and they are probably identical functions. If they have an overlap in their fingerprints, like in our example here, it is extremely unlikely that the 2 functions are similar. It can be proven that the Jacquard similarity of the 2 min hashes is a good approximation of the Jacquard similarity of the 2 sets of n-grams. So, given that min hash similarity is much faster, these are going to be our similarity metric from now on. Now to the last and most critical part of our approach, making the ranking process fast. If we just replace the original fingerprints that capture opcode frequencies with min-hash fingerprints, it wouldn't solve our problem. The complexity of ranking would remain n-squared, while the cost of each fingerprint comparison would increase. Certain intersections are more expensive than just subtracting 2 vectors from each other. Thankfully, min-hashes are not really meant to be used for exhaustive search, but for locality-sensitive hashing, a kind of hashing where similar items are likely to be placed in the same hash table entries. This is how it works. We'll limit ourselves to just 3 functions to make our lives easier. The colored box next to each function represents its min-hash fingerprint, with each color indicating a different value. During initialization, we would use these values to associate each function with a hash table entry. First, a pointer to F0 would be placed in these entries. Then F1, it has no overlap to F0, so a pointer to it would be added in these extra entries. And finally F2, its fingerprint is identical to that of F0, so it would be placed in the same table entries. During ranking for F0, instead of trying all functions, we would just check the hash table to see which other functions map into the same entries. By definition, these functions have at least one identical min-hash value, so they could be similar. Functions with no table entry overlaps, on the other hand, have completely different fingerprints, so they would have 0 similarity with F0. Skipping them accelerates ranking with no negative impact on the quality of the selected pairs. In our example, the only potentially similar function is F0, so we select it, we calculate the Jacquard similarities of the 2 min-hashes, and we continue with the rest of the process. The approximate complexity of this search is n raised to the 1.5 times k, where n is the number of functions and k is the size of each min-hash. This scale is much better than the original exhaustive search, which was n-squared. One more way we can reduce this overhead is by adapting the size of the min-hash fingerprint, the number of functions in the program. Reducing the min-hash size makes it more likely that we will fail to examine similar pairs, that we will fail to consider similar pairs of functions, but that makes ranking faster. For larger programs where ranking dominates the runtime, the speedup is usually worth the risk of missing some merging opportunities. So in those cases, we reduce the size of the min-hashes. How exactly we do that? The details are in the paper. We will not discuss it in this presentation. We have implemented all this in the latest LLVM. Well, what was the latest LLVM when we submit the paper? The code is publicly available on GitHub and in our artifacts, links for which are here in these QR codes, and again, we provide the QR codes at the end of the presentation. Let's see now some evaluation results. The first one is about the quality of the fingerprint itself, how well fingerprint similarity correlates with alignment. On the left is the same plot we saw earlier, a heat map of F3M similarity versus alignment ratio values for all 800 million function pairs in Linux. The plot on the right shows the same information but for the new min-hash fingerprint. We see that points are closer to the diagonal, indicating a higher correlation, 62%, which is not perfect, but it's a huge improvement over the 20% for F3M. At least some of this disagreement between the two metrics is artificial. For example, in the upper left corner, we have 140,000 pairs with zero fingerprint similarity but perfect alignment. All of these pairs are functions which contain only one return instruction. And the problem stems from how our ranking and the alignment algorithm treat return instructions with different types. The ranking treats them as dissimilar, the alignment algorithm treats them as similar. While this lowers the correlation, it does not really affect us because such pairs are never merged. Their profitability is the same as their fingerprint similarity, which is 0. Much of the improvement in correlation, and in my opinion the most important benefit of the min-hash fingerprint, is pushing all these pairs from the lower center and right towards the lower left corner. These function pairs are almost definitely unprofitable, but we couldn't tell that using the old fingerprint similarities. Even if we used an approach similar to locality-sensitive hashing, we would not be able to remove these pairs from the ranking process because according to their fingerprints, they are similar. We would have to waste time dealing with them, no matter what. With a new fingerprint, we know their similarities are low, so we can safely ignore them in the ranking. This is where much of the speed up of our approach comes from. Speaking of which, this is the compilation time results for all our benchmarks. The benchmarks on the x-axis are ordered by the number of functions in the code. What we measure is the compilation time from linking all the LLVM IR files together until the final binary is produced. We do that because function merging has knock-on effects on later stages. If it reduces code size significantly, later stages will run faster. The results are relative to using no function merging, our baseline. For most of the smaller benchmarks, there is really no significant performance difference between F3M and F3M. Only a small portion of their time is ranking, so accelerating that has no effect really. There are 4 cases with significantly worse compilation times, but the only one that seems actually scary, numbed, is actually a side effect of having a better fingerprint. In this case, we find a few more profitable pairs of functions than before, leading to a higher merging overhead. And I would argue that this is actually a good result. We waste time because we do more profitable merges. Finally, all the large programs, anything with more than 9,000 functions, benefits from our approach. The more the number of functions, the more significant the speed up relative to F3M. On the left end, it's only a few percentage points, but on the right end, for Chrome, we reduce the compilation time from 46 hours down to approximately 2 hours for our static policy and 100 minutes for our adaptive one. Most of this time is spent on passes other than function merging, so the actual overhead of our approach is about 25% and 1% respectively, instead of 2700% for HiFM. On average, our two approaches are faster than the no-merging baseline by 3.3% and 5.6% respectively, which is a very, very good result. I could go as far as saying that function merging is now for free, but I did that with the HiFM paper and that did not age well. Improving code size was not our primary objective, but we did end up with slightly better results. The plot here shows the code size reduction relative to the no-merging baseline. Most of the benchmarks show no change, and there are a few cases where we get worse results, but it's usually only a couple of percentage points, not more than that. For 17 benchmarks, the improved fingerprint similarity leads to more successful merges and less code size. The best case in terms of relative improvement is Imagic, where we go from 13% to 70% code reduction, while the best case in terms of raw code size reduction is Linux, where we reduce the binary size by 500 kilobytes. On average, we deliver 0.4 percentage points more reduction using the static approach and 0.3 percentage points using the dynamic one, which is pretty good for a side effect. So this was our work on a better function merging. Our approach improves on the state-of-the-art in all regards. It makes function merging orders of magnitude faster for large programs, up to 600 times faster than HiFM, and 5.6 times faster than no function merging on average. We do that without compromising on the quality of the merging. We actually produce smaller binaries on average, reducing their size by up to 500 kilobytes. We achieve these results by using better metrics that better capture the potential for code merging, and also by using a more intelligent matching process that ignores unprofitable function pairs. Overall, this leads to an approach that makes function merging realistic even for large programs, delivering its code savings in minutes instead of days. Thank you.